So we're very lucky today to have Roberto Magalotti, who's the new Director of Acoustics Research at Bowers Wilkins. He was previously Head of Research at B&C Loudspeakers, which is a very large and well-known PA manufacturer that many of you may have heard of. Previously studied physics in Bologna, and teaches electroacoustics at a couple of different institutions. So over to Roberto, thank you.
Thank you for the introduction. Welcome to you all. I have two presentations today. One is a very small one to begin with. I want to show you something about the use of simulation in loudspeaker design. And that's a very short one, just to give you a glance of how tools like console are being used in the loudspeaker industry. And then I will get to the main topic today, that is about room acoustics and modal decay times. So this first presentation is basically divided in two parts that have something in some way mirror two parts of my career. The first one is about loudspeaker drivers, and as you know, most of my careers was in the pro audio environment, and the second one is on loudspeaker systems, and this has more to do with my work at Bowers Wilkins. So, first off, if I turn this on, yeah. It works. Loudspeaker drivers. Loudspeaker drivers are a complete physics book. You have chapters in acoustics, mechanics, electromagnetism, heat transfer, and so on. Okay? So, just a few examples of how you can use simulation tools in the design of loudspeaker drivers, starting from electromagnetism. This is an example of the design of a loudspeaker motor with its voice coil. The color map shows you the intensity of magnetic flux density inside the motor. This part here is the magnet. The other parts are the polar expansion, the iron parts. And the gray lines are the flux lines through the structure, and you can see the voice coil represented by this item, and you can see the Lorentz force that is pushing the voice coil when a constant electric current is flowing through it. I don't know if you can see clearly the arrows, but it's easy to see that the voice coil gets the maximum of force only when it is fully inside the air gap, and otherwise only the part of the coil in the gap gets a significant amount of force. And this is the main physical reasons because why the so-called force factor of a loudspeaker changes with the position of the coil. If you've probably seen things like this before. Another field of application is mechanics. This is an example of an eigenfrequency analysis of a loudspeaker dome. In this case, it is the dome of a compression driver, and at these frequencies, you get all kinds of resonant behaviors out of those domes. And of course, you need to take measures to reduce the impact of those behaviors on the radiated sound. Third example is about acoustics. This is a well-known type of waveguide, acoustics waveguide, and the main goal of this device is to convert an initial plane wave coming out of a small disk, and again, this is typically the output of a compression driver, and convert it to a cylindrical wavefront. And as you can see, if it's not perfectly cylindrical, it's quite a good approximation. Okay. Going to loudspeaker systems. And the loudspeaker system example are pretty Bowers and Wilkins, actually. One of the things that we take into account is decoupling the loudspeaker drivers from the enclosure, because having the enclosure rigidly coupled to the driver tends to transmit the vibration to the sides of the enclosure, and having all sorts of secondary sources that are interfering with the main sound emission, while if you manage to decouple well the driver from the enclosure, this kind of effect is minimized. It can never be completely removed, but it can make a significant difference in sound quality. The second example is about the effect of a cabinet. What you see here is the mid-frequency part of a loudspeaker system. We tend to put our mid-frequency drivers in a thing that we call a turbine head, a nice and round and smooth type of enclosure. And as you can see, when you only have this kind of head, the output of a sound pulse is very clean, while when you add the cabinet, you have some sort of diffraction and reflection effect that you need to consider. And my last example is about the use of a different technique, because all the previous ones were with finite element method. This one is with a boundary element method, that the kind of the technique that you use when the ratio of the wavelength to the size of your system becomes too large for FEM, okay? So with this kind of technique, you can evaluate the propagation of your sound wave across all your surfaces, and this allows you to do different things. For example, you can zoom in and investigate in more detail what happens between the top of your cabinet and the HF head up here. Or you can zoom out and investigate how this behavior translates to the propagation of sound in the surrounding environment. Okay? So this is a very short introduction, but it was intended as a first glance in the use of simulation in loudspeaker design. Now, the main topic of my presentation today is simulating and measuring modal decay times in rooms. This is a work that has been going on for several years. And we were trying to investigate the interaction between loudspeakers and rooms, especially in the low frequency range, where you have isolated modal resonances in a small room. And we tried to develop a better model of what happened in small rooms to have a better understanding of this kind of interactions. So what I will show you is basically divided in three parts. The first is about simulation, the second is about measuring, and the third one is about matching the two. So first I will show you something about the interactions and relationships between the modal decay times, so the decay times of single modal resonances, and how they relate to boundary conditions. Then I will show you something about how you can measure the response of a certain room and how you can extract this kind of information, modal decay times, from a pretty classical room impulse response. And then I will try to show you some examples of how those simulations and those measurements match in real environments. So that's the first part is about defining decay times and setting appropriate boundary conditions. I will do it very step by step, starting from very simple examples, so it will be easier for you to tell me where I'm wrong, because I'm not a room acoustician, so I might say wrong things here and there. The first one is the simplest example that I could think of, reflections in a duct. We have a closed duct, meaning that the impedance at the far ends of the duct is much larger than the impedance of the medium inside the duct. The basic assumption is that the sides of the duct are perfectly rigid walls, infinitely rigid walls, so there's no loss of energy through the sides. And we want to understand how fast the energy of the sound field gets out of this very simple system. Now, if you plot the time history of total sound energy of a system like this, you end up with something like a staircase, okay? Because basically, if you have a very concentrated impulse, all the energy is concentrated in a point, so you have no loss of energy while the impulse is traversing the duct, and you have a loss of energy only when it hits one of the ends, okay? So you have a certain amount, you lose a certain fraction of your total energy at each impact, and you can always approximate a behavior like this with a continuous curve that is going to be an exponential decaying curve, okay? And this means that if I were to plot instead this fraction of energy on a log scale instead of linear scale, or express it in dB, that is exactly the same thing, this one would become a straight line, and my decay time would be proportional to the slope of this straight line. If we analyze the situation from a point of view of frequency instead of time, what we get is a harmonic series of resonances that are related to the length of the tube and, of course, the characteristics of the fluid inside. So we are going to have a picture more or less like this. We have several resonances equally spaced in frequency and all with the same decay time. How can we approach the computation of the decay time? Well, we have at least two possible strategies here. One is to resort to our favorite software tool, okay? And do eigenfrequency analysis. This one is in a room, not in a duct, but the idea is exactly the same. The typical approach here is to do a sound hard walls infinite impedance analysis, and you get a simple eigenfrequency like this, 34 and something. But if you add a finite walls impedance, this frequency becomes complex, and you get an imaginary part of the frequency. And there's a very simple relationship tying this imaginary part to the modal decay time. Now, about the modal decay time itself, the most common definition is inspired by the reverberation time. So it's the time that it takes for the energy in the sound field to decay by 60 decibel. So this is usually called modal decay time. It's MT60, and this is the complete formula that you need to know to convert this to a time in seconds, okay? Or we can go back to our duct example and work from first principles, because from this picture, we know that we have basically two elements that are impacting our modal decay time. One is how long is the duct, how much it takes from one impact to the other. And the second one is the fraction of energy that is lost at every impact. And this can be very easily computed from 1D equations. And the result is something like this. Don't be surprised if you see the same 3 logarithm of 10 here, because it's due to the definition of decibel and the definition of MT60. But what the formula says is that the modal decay time depends linearly both on the length of the duct and the normalized impedance at the ends. This ZW means that I have normalized the specific impedance to the characteristic impedance of the medium, so it's Rossi, okay? But this leads to a very simple formula here that can be used this way, or of course the other way around. If I want to set up a simulation and see if my MT60 is as predicted, I can use this to compute the impedance that I need to assign to the walls, okay? The good news is that the two strategies lead to the same end result, meaning that if I use this formula and I input this again in my favorite software tool, which is a pretty simple thing to do, you have this impedance that by default is the characteristic impedance of medium, so you only need to multiply this by the normalized value, okay? And what results is exactly the picture that we've seen earlier with equally spaced harmonic modes and the same decay time for all of them. But ducts are not that interesting. Rooms are much more interesting than ducts. So let's go to 3 dimension and pick some form of interesting room. That's a rectangular room of more or less typical value, okay? It's 17 cubic meters. The size of the dimensions of the room are chosen so to avoid degeneration as much as possible, so there are no repeated frequencies below 100 Hertz. And when you have a room instead of a duct, you have many more modes, and you can even classify modes in different families, so to speak, okay? So you see here all the frequencies of the modes in this room. This triplet of integers is called the mode index, and it tells you exactly how many nodal planes you get in each direction, each of the 3 directions, x, y, z, okay, for the corresponding modal frequency. Let's go into it a bit more. These are the graphical representation of all those modes, okay? We are talking about stationary waves, so we have positive pressure on this side, negative pressure on this side, and the nodal plane where the pressure is always 0 when you have this kind of resonance. The typical classification of these modes splits them in 3 categories: axial, tangential, or oblique, depending on the number of axes that are involved. You talk about axial modes when you only have one family of nodal planes. You talk about tangential modes when you have 2 families of intersecting nodal planes, and oblique modes when you have all 3 axes involved, okay? These can be further subdivided according to the actual axis involved. So we have three different families of axial modes in x, y, and z, three different families of tangential modes, xy, xz, yz, and one family only of oblique modes. Okay? We will see that the classification has actually a great importance in predicting the behavior of each of those resonances. So the first thing that I want to do here is to apply to my room exactly the same boundary condition that I used for the duct. Okay? So I will make the walls that are perpendicular to the x-axis absorbing and leave the other ones perfectly reflecting. Okay? And see what happens to my room modes. This table repeats the table that we've seen 2 or 3 slides ago, with the addition of 2 columns. One is category, so what kind of mode is in there. And the second one is class, so the further subdivision in axial x, axial y, axial z, and so on. And in this situation, the decay times of the modes in my room have this kind of behavior. So I have highlighted with red circles the same modes that we've seen in the ducts. And as you see, there are many other modes that share the same decay time. But there are other ones that have exactly twice the decay time of axial mode in X. Now, I have highlighted here the axial modes in X. They are exactly the same that we had in the duct. And now I will highlight those modes that have double the decay time. And ask you to guess what is the shared features of those modes. They are not all of the same category. We have axial modes in there, we have tangential modes in there, no obliques. Okay? But the only thing in common here is the 0 for the x value of the mode index. Okay? So only those modes that have 0 here get twice the modal decay times. And this means that we have halved the absorption in this case. We'll get back to this. Now, I want to try and do something different and try to build a uniform situation in this room. So in this second example, I will try to use my formula for the impedance on all 3 axes, okay, with the same starting MT6, but of course each pair of walls will have a different value because of the different values of room dimensions, okay? So I will have a certain value of impedance here, a different value of impedance on the Y walls, and a different value of impedance on the Z walls, this one that I can see and the floor that I cannot see here, okay? So what happens in this situation? Well, in this situation, I get a picture like this. I managed to get something right. All axial modes have exactly the same decay time. But there are 2 remarks. First of all, the decay time has become half what it was before. And this means that I have doubled the absorption. And the second remark is that tangential modes all have the same decay time, but it's less than the time of axial modes. And oblique modes have an even smaller decay time. Okay, to explain all of that, I need two different developments. The first one has to do with the difference between specific impedance and total impedance. Specific acoustic impedance is the ratio of sound pressure to particle velocity, okay? And it's the kind of acoustic impedance that I've been using until now, and it's the one that you see in those formulas. But we loudspeaker designers, when we use acoustic impedances in equivalent circuits, like to use a different kind of impedance that is called simply acoustic impedance or total acoustic impedance. And it's the ratio of sound pressure to volume velocity through a certain surface, okay? So I want to show you what happens if I convert those formulas to total impedance. What I need to add as a element is the surface, okay? So the total acoustic impedance in this case is the specific impedance divided by the surface of the wall perpendicular to X. But look what? Length and surface end up in the same place. So my total impedance only depends on the volume of the room. The same thing happens with the other axes, okay? So in the end, I can say that my situation, my uniform room, means that all walls share exactly the same total acoustic impedance. I have 6 equal acoustic impedances in parallel from the point of view of the internal sound field, okay? For the second development, I need to call a recognized authority, and that's Moore-Singard Theoretical Acoustics. There is a very nice chapter on closed cavities and modes in closed cavities. And in this chapter, you find this formula that appears a bit intimidating at first glance, but it's very similar to what we've seen until now. This is a formula for the wavelength, for the wave number of a mode, not the wavelength, the wave number of a mode here, divided in a real part and an imaginary part. You know the wave number is strictly linked to frequency. One could say that it's the special version of frequency, so there's the speed of sound involved. But the same thing that we saw earlier with frequency is true with wave numbers. So the imaginary part is the part that is linked to decay time. So we are interested in this parenthesis in here. There is another difference between my notation and Moore-Singard notation. They are using admittance instead of impedance. So those beta are the admittances of the 4 walls in our rectangular room. But as you can see, each part has the relevant dimension of the room in it. The new element is this thing here. This is called the participation factor. And the rule is that the participation factor is 1 when the mode index number for that dimension is 0, and it's 2 when it's different from 0. I will leave to them to explain the thing. The effect of the factors epsilon, nx, etc., is to make the first order effect of the admittance of a given wall, read absorption, just half as large for those waves moving parallel to the wall as it is for those waves which reflect from the wall. Okay? Now, if I can manage to do that, I want to get back to some previous slides, because this explains a lot. We have seen that here, the modes that move parallel to the walls have twice the decay time, and that's the reason. It's the participation factor, okay? They only feel the effect of half the admittance we've put in there. And the same thing happens when you add absorption to all the other walls. So for an axial mode, 4 walls that are on the side, that are parallel to the main direction of propagation, have the same effect as 2 walls on the direction of propagation. So we have doubled the absorption by adding 4 more walls instead of 2. Okay. So now we can translate Morse and Dinger to our language and write this. Okay? This comes directly from Morse-Ingard and the way we were writing MT60. In a rectangular room, for any mode, you can compute the modal decay time from this if you only put the correct participation factor in here. Okay? Now, the form of this equation might sound familiar to some of you because it is very similar to a very famous one. Right? What changes is that in Sabin's formulation, we have absorption coefficients here. And here we have admittance, and we have the participation factor. But I find comforting the fact that they are formally similar, because this thing up here should really converge to this one in high frequency. Another difference is that here I am summing from 1 to 6, and I know my participation factor from Morse and Ingard, from theoretical acoustics. What I would really like to do is to generalize this approach and use it for a general geometry. So from a formal point of view, this is pretty easy to do. I simply remove the sum from 1 to 6 in here. Okay. And I say that I extend the sum to all the surfaces, all the bounding surfaces, all the boundaries in my generic geometry. But of course, I am left with the issue of computing those participation factors. Well, the good news is that it's easy to do this if you have some simulation tool that gives you the modal functions of your resonances. So you can compute the participation factors in general from the form of your modal eigenfunction. You pick your modal eigenfunction, you decide what surface in your generic room you want to investigate, and you can simply take the square of your modal eigenfunction, normalize it with something that is an integral across the whole volume, and then average it on the surface of interest. And from this, you can get different participation factor for each mode and for each surface. Good. Enough for theory. Let's do something more practical. Okay, I have a real room. I can measure the room impulse response. How can I get the modal decay times from a real measurements? Well, the solution that we have applied in this case was to use the wavelet transform. The wavelet transform is a form of time frequency analysis that is based on this kind of basis function. Now, I might say something wrong. I know these functions mostly from a practical point of view. I don't know exactly the theory behind that. But the good thing about this kind of wavelets is that you can tune them to a certain central frequency that is basically the sinusoid that is in here, and then you window in a Gaussian shape, and of course you have the usual trade-off between time and frequency. So you can get a short time wavelet that have a larger bell in the frequency spectrum, or a longer one in time that gives you more selectivity in frequency. And you can play with this value and see what changes. And I want to show you what changes here. One thing I haven't tried is how to start okay, this is a wavelet transform of a room impulse response. There's a color map. The more white the color means the highest the energy content. You have a frequency axis here and a time axis here, okay? So it's second and hertz and level coded in color. Let me see if this starts. No. Wrong one. Excuse me?
Is it disabled the mouse?
Yes, it has. I'm afraid it has, so maybe I can do simply this. And use the mouse to start. Come on. Where are you? Okay, now I start changing the bandwidth and make it narrower and narrower. Ah. Nope. Back again, please. Yeah. Okay. So you start seeing the modal resonances appearing down here. So the more you narrow the bandwidth, the more selective you become in frequency, but the more smeared in time becomes the energy, okay? So here you can find your optimal balance of time selectivity or frequency selectivity. And if you look at the movie again, you will notice that the first isolated mode become clear and easy to analyze much earlier than the other ones. And this means that basically any mode has its own optimal bandwidth. There is no common solution that works well for all the modes in the room, okay? So, based on those remarks, we have developed a method. And the first step is to find peaks in the FFT of your room impulse response. These, of course, the ones that I will show you are all bad rooms. So modes are very clear. There are sharp peaks. It's not difficult to find the modal frequency. You can pinpoint them even with very simple method. Once you have decided what is the mode that you want to investigate, you can do a product in frequency domain, meaning that I'm using the wavelet, the frequency version of the wavelet, as a filter, tuned to one single modal frequency, okay? And the product of those two functions will give me something like this, okay? Then I take this from the frequency domain, and I do an inverse FFT to get a decay curve. I will get an answer, a response in time that will be, generally speaking, a complex one, so with real and imaginary part. And I can compute the energy at each point in time and retrieve a certain decay curve. Or I can actually retrieve different decay curves depending on my optimal trade-off of selectivity in frequency and in time. As you see, if I use a wide bandwidth in frequency, I get this kind of decay curve when I have lots of beats with neighboring modes, okay? So it's difficult to find a clear decay time here. I can go all the opposite way and get the blue curve that is very, very selective, but it becomes too smooth and tends to not have a clear straight line somewhere. And generally speaking, the optimal solution is something in between, where I can get a clear decaying straight line somewhere in the response. Now, to retrieve the actual decay time, we have tried two different methods, and I will show you them both if I can start movies again. Okay. The first one is a linear fit. So in this case, I am trying to fit simply a straight line to the decaying part of my curve. I will start the movie, and nothing is going to change here, nothing is going to change here. I invite you to direct your attention here and here. In those two parts, you will see the effect of a narrowing bandwidth in the frequency spectrum and in the resulting decay curve. Okay. In the end, the program tries to use a figure of merit here to find the best compromise and compute a modal decay time, in this case 2.553 seconds. The results, here it is.
No line feed
Okay, same idea, different method. The end result is likely very similar to the previous one. Okay. So, as a recipe, the computation of MT60 times means simply measure the room impulse response. We did it with a loudspeaker and a microphone. And for each mode, you can find the central frequency. You can compute a set of tuned wavelets at the right central frequency. Find the best bandwidth of your wavelet function or transform or filter or whatever you want to call it, and fit the decay time. Now, does this bear some resemblance to what you measure in a real room? That was the important question. And we managed to measure several different rooms. I will show you 3 examples. The first one, the smallest one, was a rehearsal room for music. That's the closest thing I have ever seen to an ideal rectangular room. Okay, it was in gypsum board, but it was still being built, so there was no absorption in there, and it was perfectly rectangular. So we managed to get a good fit between simulation and measurement by using simply 3 values of acoustic impedance at walls, and using the theoretical values of participation factor from Morse and Ingerd. And the result is, no, this is not working. Okay, this is the result. It is not perfectly aligned, but it gets most of the ups and downs of the actual modal decay times. Okay, and this result was obtained with these values of the wall impedance. What I find interesting and realistic, at least, is that the rehearsal room was isolated in the middle of a much larger room, so the only point of contact was on the floor, and the couple of walls that include floor and ceiling were the ones. Okay. Gone? Those. Okay, so the highest normalized impedance was for floor and ceiling. then there's a detail on mode degeneration, but I think I will.
Two surfaces. When you say floor and ceiling, would that
Yes.
be an average between the floor and the ceiling?
I mean that I've been using the same value because in a rectangular room you cannot tell how much of your absorption comes from one or the other. You could have the same value on both parallel walls or all the absorption on one walls and absolutely nothing on the other one, and the result would be exactly the same. So you cannot tell this. So I've been using couples of walls, at least in rectangular rooms. Okay. The second example is a test chamber at BNC speakers, and in this case we have found that adding the door as a fourth group of surfaces improved the fit between simulation and measurements. You see there is a bit of a slanted wall down here. It is not perfectly rectangular, it is nearly rectangular. But by fitting 4 different impedances, you can get something like this. So you see, the idea is to find a type of modeling that can give you something similar to the acoustic fingerprint of a certain room at low frequency. Okay? So even if you have some miss here, for example, or not exactly nailed values, the overall landscape is reproduced reasonably well. And these are the values that we used. Once again, floor and ceiling was by far the most rigid part, and the door was the weakest link. Okay? So the smallest impedance of them all. The last one is, I should say, a bit of a stretch, because we tried to do the same thing with the reverberation room of the University of Bologna. It's a very large room. It's 12 meters on the longest side. It has a very complex shape, especially the ceiling. It has some beams in it, slanted walls and everything. And we have tried to match simulation and measurement by using, again, only 3 different values of impedance. That is probably a too small a number of parameters for such a complex environment. But despite that, again, the overall picture looks more or less reasonable. And these are the values that have emerged from our simulation. I am not completely happy with those values because there's more than an order of magnitude between the largest and the smallest, okay? But again, the smallest, the third one, is for the walls that include the room, the door to the room, and they were recently built walls, while the other 3 walls are in sound concrete. So it's not completely unreasonable. And it probably gets in the picture the fact that this ceiling is very complex, so generally speaking, the waves do not hit the ceiling perpendicularly to the surfaces. So there's a lot of surface on the ceiling compared to the effective area. So there's room for improvement of the model up here. And that is basically all I had to tell you. My last slide is the presentation that I did in the last year. This is more or less a collection of 4 different presentations from late 2018 to 2019. The last one was at the AES convention in New York. So you have those if you want to go a bit more into the mathematical details of of everything, and that's it for me now. Thank you for your attention.
Well, Philip.
I was going to go right back to the beginning almost. So, if you've got a loudspeaker on, like a stand, for example, how much effect does the stand have then on, I guess,
The loudspeaker.
Yeah.
We've been working on that for the last 4 months, I think. Yes, the stand is important in the overall behavior of the loudspeaker because it can have its own resonances, its own acoustic emission. So we are always trying to minimize the effect and improve go closer to the theoretical behavior of the loudspeaker as a point source without interaction with the floor. So it is, I mean, we are doing eigenfrequency analysis, we are doing acoustic power computations, and it all goes in the stands that you get with our loudspeaker systems.
Yes.
I just, your modal decay calculation from the measurements.
Yes.
Fitting a curve is notoriously difficult to the actual amplitude curve.
Yes.
One of the things most of the instrumentation we use does is do something called Schroeder reverse integration. I'm wondering if you tried that.
Yes.
So you start and basically go integrate backwards in time from the end towards the beginning.
Yes, we tried it and we didn't like that a lot. We didn't like that a lot because Schroeder integration is good but tends to put everything together. I mean, depending on your noise rejection algorithm and depending how noisy it is, I mean, I have found it much easier to fit the decay curves coming from wavelet transfer than Schroeder integration, based on exactly the same.
I was meaning on the waveforms you got from the wavelet transfer, because you sort of use that, if you like, to pull the signal out of the noise. I'm just wondering, you then integrate it backwards, you get a better straight line to look at.
My personal experience is that I got a worse
Okay.
straight line segment.
I don't think it's appropriate actually, because Schroeder reverse integration is to convert from impulse response measurements to interrupted noise measurements. And modal decay time for a mode, which is for deterministic excitations, is slightly different from noise excitation.
I just was curious.
Yeah, no.
Yeah.
I mean, but I think I've got the answer and tried it.
Could you see this method being applied to structures to get loss factors of modes rather than room NTC?
Absolutely, yes. I'm not very familiar with structural analysis, but it's basically the same playing field. You have resonances, you have some amount of damping, and you want to fit the frequency and the Q. What you can do sometimes, if you know the modal functions in advance, is a smart use of your microphone position, so you can split the generate modes in different measurements. In this case, it was the rehearsal rule, okay? So the modal functions were very simple, nodal planes everywhere. I had 5 microphones, and in this case I managed to put 2 on them on the nodes of one mode and 2 on them on the nodes of the other modes.
Okay.
They were exactly at the same frequency. One had 1.25 seconds, and the second one had 1.75. And it was extremely clear which is which.
Trevor?
What happens in a room which has got a decent amount of bass absorption in there for treatment? So you're getting much more modal overlap and the Q is much smaller and things are more mingled.
Well, modes become more difficult to pinpoint, but we managed to measure them reasonably well.
But so far the rooms you showed were relatively low absorption there.
Yes, yes. Of course, the reverberant room had decay times in the range of 10 seconds or even more.
So what happens if you go into an IC listening room and the decay time is half a second, let's say, at low frequency?
It becomes harder. It becomes not impossible. We have measured some recording studios, and most of the time we managed to fit simulation and measurement and have a reasonable estimation of the decay times of single modes, down to below 1 second. So it can work even in strongly damped room. Of course, not where the modal density becomes higher. But until they are separated enough in frequency,
Sort of related to that, I was going to say, speech people, when they try to decompose the formants, the modes of the vocal tract, have the same problem. What happens when they're low Q and they overlap a lot and you can't see the peak? And I noticed your main disparity in a lot of your measurements was, I think the measurements missed. You know, where there was a mode, but obviously the measurement didn't find the peak.
yeah.
There's a technique that the speech people use where they use basically an LPC model of the frequency response, and what you can do then is you can actually artificially Q enhance the actual frequency response. And the classic format extraction program, and the Canvas one does that iteratively and gradually picks out peaks, and I just wonder whether that's something you might be able to use, because obviously once you've got the peak, then you can use your wavelet filtering argument to pull that mode out of the mix to work out its decay.
That would be very interesting. That would be, yes. If you can give me some reference to
Try
that.
and find it. It's sort of it's one of those standard techniques now, but
Okay.
that was standard 40 years ago.
That was one of the problems. We had some problems with noise here and there, so sometimes we couldn't find the mode because there was noise in that frequency band. And I know there's another thing missing in all this picture, and it's the structural vibration.
Right.
I'm simply modeling a room as a set of acoustic absorbers, so nothing, the walls don't vibrate, there's nothing that can bounce back energy from outside the walls, so it's far from perfect.
I'm going to have to wrap up the formal question. I'm very sorry, at least from my perspective, because I was supposed to be at an open day over there 5 minutes ago. Just thank Roberto.